So in the last class, we have seen how to find the maximum of a given sequence of numbers. So if there are n numbers in the sequence, how many times we will iterate through this while loop? So if there are n numbers that we are in a sequence, how many times we iterate through this while loop? Right? So n iterations. So if the sequence length is n, so if you see there is sequence length is n, we iterate through the while loop n times. How many times? No, like the statement on line number 6, it is an initialization statement, right? So you execute it only once. It is independent of n. Yes or no? The statement on line 6, is it independent of the value of n? It is independent of value of n. And similarly, the statements 23 to 26, if you see, so they gets executed only once, independent of at most once. If init flag is equal to 1, line number 24 will be executed, otherwise line number 26 will be executed. So this is also independent of statements 23 to 26. The number of times they get executed is also independent of it. So if you see, that means if you take the execution time of a program, the execution time of a program is dominated by this while loop. Is this while loop? Because most of the time we are iterating. Okay, so there is this question, shouldn't it be n minus 1? Let's say we don't care about if it is n minus 1 or n plus 1, roughly equal to n. Okay, otherwise you just have to be more careful. But roughly it is equal to n. N minus 1, n plus 1, that's all right. Because, as the value of n keeps increasing, so what is, if n is equal to 1 million, so 1 million versus 1 million plus 1 or 1 million minus 1 is not going to make any difference for us. And then if you see the statements within, so like for example, so if this gets executed n times, then this statements also gets executed n times. Okay, the comparison also gets executed n times. And sometimes we go to the if part and sometimes we go to the else part. But approximately, if you see, if you take, we can say, let me put it this way. In one iteration, this whole statement starting from 10 to 20, it takes some constant time to execute, some constant time. This whole everything, this whole while loop, starting from here to here, it takes some time, some constant time to execute. It can be some, let's say it takes k units of time to execute. At most, it takes less than or equal to k units of time to execute. Is it a reasonable thing to say? And k is independent of, it's not a function of n. Within the while loop, if you see the statements from 10 to 20, we can say they take at most k units of time to execute. At most. Why at most? Because computing exact is a pain, because sometimes, you take the if part, sometimes you take the else part. Within the else part, sometimes the if condition could be true, sometimes it is false. So exactly measuring that execution time would be a pain, but roughly we can say there is some constant k, and the whole statements 10 to 20, they take at most k units of time to execute. And let's say this takes some constant time. Let's say that constant time, let me call this as k1, this is k2, and this takes k3 time, at most k3 time to execute. So all these case k1, let me, all these case, they are independent of n. This is k1, k2, k3, they are independent. No, because the if statement, no, so if you just look at 10 to 20, that is one iteration of the while loop, it is independent of n. No? One iteration of while loop is, it is independent of n. So if you take overall program execution time, the overall program execution time, if you overall program execution time, if you see, this is equal to k1 plus nk2 plus k3. Or it is, we can say, if not equal to, it is approximately equal to or bounded by this. Are you with me here? Are you with me here? The overall execution time, here either we can use equal to, or even we can kind of use less than or equal to also, we can use approximately. So what happens is, as the value of n increases, no, what happens is this k1 and k3 terms, they are not dominant. This is the term that is the dominant. Yes or no? This is the dominant term, right? As the value of n increases, if n is equal to 1 million, 2 million, 3 million, this term becomes dominant. The other two terms, they are not going to uh, impact. So in fact, if you take the ratio of, if you take the ratio, yeah, so let's keep it that way. So for the time being, we'll just restrict our discussion to this, that if you look at the execution time, so k1 and k3, as the value of n increases, the other two terms, they don't contribute much. The middle term will be the dominant nk2. And this constant k2, it depends on many things. It depends on the processor in which you are executing and things like that. Like for example, one may have 2 gigahertz processor, a processor running at 2 gigahertz clock speed, and someone else may have a processor running at 3 gigahertz clock speed. Or some may have Intel Xeon processor, and someone else may have Intel Core i7 processor, and someone else may have Core i5 processor. So depending upon which processor you are running, etc., this K2 could keep changing. But what remains is N. Yes or no? Are you all with me here? In this whole thing, the most important thing that we should understand is, this is kind of invariant. This is the one which kind of remains the same. It is independent of the processor on which you are executing the program, and it depends on RAM also. Good question. So, but n, so this factor n does not depend on RAM. The constant k2 could depend on RAM. So, if you want to characterize the program in a machine independent way, you can say this program execution time. I'm using PET as a shorthand, is proportional to n. Is this a right thing to say, that the program execution time is proportional to n, or approximately equal to n? So, great. So now let's move to the next problem that we looked at in the last class. That is, so here we are trying to find sum of first n natural numbers, sum of n first n natural numbers. So here again, the number of iterations is, so there is some time, like for example, so we don't even want to consider the printf and scanf times, so because it depends on how fast you enter the input. Or let's see here in this program, let's ignore the input and output statements and just focus on the compute part, where we are trying to compute the sum of first n natural numbers. So here, if you see the, so let's say these two statements, they require at most k time units, k units of time. Then if you see the overall program execution time, the overall program execution time is no is kind of less than or equal to nk, because we will be iterating this, the for loop iterates for n times approximately. And so again, this constant k, it depends on the processor, RAM size, and many other factors. But independent of which machine that you are working on, this factor n is going to remain there. So PET, it's not a standard abbreviation. PET stands for program execution. So we can safely say that the program execution time is proportional to n or bounded by. So when you write programs, why it should be greater than or equal to nk? Or it's in this particular, in this case, let's say it is proportional to nk actually. So this is a safe statement to say. Let's not get into those things. This is a very safe statement to say. I'm using less than or equal to program execution time is less than or equal to k, because we are assuming this takes at most k units of time. So all right, so this is an approximation. We are just trying to see, get a sense for how the program execution time kind of varies as the input length increases, how the program behaves. Great. So now let's, so here one interesting thing about this program is the amount of, what is the amount of space required, amount of memory required in this program. Let's take this in this program. Yeah, okay. What is the amount of memory required in this program for to store data? Yeah, so here you can see the amount of memory required is 16 bytes. We are using four variables and 16 bytes. And so is it independent of space requirement, program space? So space required, space required is constant. Required is equal to, and it is independent of the value of n, right? Yes or no? This is independent of value of n. And if you go to this one, while this the program to compute the mags of a sequence, what is the memory required here in this program? How much memory are we using in this program? So 12 bytes. So here we are using we are using three integers, and each integer will require 4 bytes of memory. So in this case, the memory required is 12 bytes. Is it possible to reduce this memory requirement further down from 12 bytes? Is it possible? How much we can reduce it? Yeah, so we can make init underscore flag as a byte or as a char. If you declare it as a character variable, then repeat what, Roma Harsha? We are look, yeah, so good question. So Siddiq has this question. So we are, if you take a program, so program, so it constitutes of instructions plus data. Let's say now we are focusing on data. So instructions also require memory. Instructions, but we are not talking about the number of instructions for the program. We are just focusing on the data. What is the memory required by this? So here, what is there to get confused? We are just using three variables, right? Current underscore number, max, init underscore flag. Each of an integer variable in the C language says it should have at least 4 bytes of memory. It could be more than 4 bytes also, depending upon the compiler and the architecture. So uh, so memory is RAM. Memory is, we cannot use ROM is only for BIOS and stuff. So you cannot use ROM. ROM we cannot overwrite ROM. So this is RAM. So here we are. This data, this resides in RAM. This is in RAM or main memory. Both are the same. Of course, bool also uses memory. Bool uses 1 byte. Bool uses 1 byte. Are you all with me here so far? Doing good? Great. So now what we do is, so now we will start using this new structure called as array. Okay, so let's see. So before we start using this structure called as array, um, I would like to introduce the idea of functions so that you can start using it quickly. So far you have written programs which contain only one function, that is the main function. So main is a special function because it is a required function for you to, for your program to execute. So main is a special function. And then you are using library functions such as scanf and printf to get your job done. So the functions scanf and printf, no, they are uh, written by someone else, and you are using their functionality in your program. Now let's see, let's go to, so now let's look at this program, uh, Prime. This is the program for Prime. So when we want to do things, we want to know, uh, when you have a big problem to solve, it will be great to kind of decompose our whole program into multiple subparts and then work on each subpart nicely. Like for example, so here if you see this code for the function main, no, for the program main, so there is input here and then there is, there is output here, there is computation, so everything is mixed up. So even for a small program such as compute, checking whether a given number is prime or not, so this code is all mixed up and it will be hard for you to debug this code, and it will be hard 1 year down the lane. If you revisit this code, you will be staring at the code trying to recall what you are trying to do, and you're back. And then if you're working in teams, no, then if someone else has to modify your code, he will be again scratching his head on how your how your program is organized, what is your logic, etc. All right. So here, so in order to solve this, in order to uh, take care of some of these issues, we want to decompose our program into functions. We want to decompose our program into functions. So just like this, if you look at this function main, you see this keyword void. That means this function main, it doesn't return anything. Every time when we call a function can return something. And if it is returning something, what is the data type associated with that return value, we need to specify. And then the function could be taking something as parameters. Some parameters it could be taking. Again, in this particular case of main, the function main is not taking any parameters. So when it is not taking any parameters, it is called as void parameters. If you leave the bracket empty, then automatically it means it's a void. So let me let's not get here. We will stick to this. And so what we want to do is, now we want to modularize our code. So what we want to do is, so the particular way we want to do is, we want to read and read. This is our big picture. We want to read a number and check if n is prime. And then finally output. This is what we would like to get. So here from line 11 to line 16, we are reading the number. We are reading the number. So here, so the first function we would like to do is, we would like to read n. So we want to write a function called as read n. So read n, it doesn't take any parameters, so it is void, but it returns n. It returns an integer. Whatever the value it has read from the keyboard, it will return. So here, this whole code, Control X. So the code which is there in the main before, now it will come here. So when we call the function readn, we don't need any parameters. And then what happens is the statements of the function readn gets executed. And if it successfully reads a value, whatever the value it reads, it should return in. So when you call the readn function, so let me comment out this whole code. I'm commenting this whole code from line 23 to line 38 so that we can run this. So this is one advantage of working with functions, that we can kind of write modular code. So you'll say n is equal to readn. And then we can say printf input n is equal to %d/n. Are you all with me here? Are you all with me? This is printf. Thank you. So now let's compile this code. Let's compile this code, gcc prime func.c. Good. So we're all good, right? And then when we say 30, it just prints 30. So if you want to see what is happening here, let's see GCC minus G. Let's try to GDB this program. So GDB A dot out. And then we will have the breakpoint at main. And then I'm using TUI run. So we can see the control now is on line number 21. The control now is on line number 21. Are you with me? We are right now. How we are doing GDB? I hope you are comfortable. Are you all with me here? So one interesting question which Narayana is asking, which I kind of didn't say, it's very, very important to understand. It's very, very important to understand the n that you are seeing on line number 6, the variable n that we are seeing on line number 6, and the variable n that you are seeing on line number 22, there is no relationship between them at all. There is no relationship between them at all. So the variable n, so here what is happening is we will see on line number 24, when we call the function readn, so we call the function readn, so control transfers to the first instruction of readn. And then this gets executed, and when so when we read something, it gets read into this variable n, and the memory that is allocated to this variable n and the memory that is allocated to this variable n, they are completely different. Are you with me here? This n and this n, they don't have any relationship between them at all. So in fact, we say the scope of this variable n, the scope of this variable n is so the scope of this variable n is this whole function, and the scope of this variable n is the function main, and these two scopes, they don't interface with each other. This is what is called as a local variable. N is a local variable. So thanks for reminding me to use the right word. So this n is a local variable for the function readn, and these three are also local variables for the function main. And the scope of these local variables is the function in which they are declared. Are you all with me here? I will show, I want you to understand that in every function, we declare variables, and these, depending upon the logic, and these variables are called as local variables. The important keyword for you to remember is this new idea called as scope. The scope of a local variable is the function in which it is declared. The scope of this int_n is this whole function in which it is declared. I want you to hold on to your questions. I want you to take one concept at a time. The first question that I want you to be with me is, are you with me on the or are you with me on this idea of scope? And this need not be n, this can be anything. So I just used n, like for example, it can be, like for example, it can be m also. It doesn't matter. There is no relationship between the original program and this, the readn function, and the main function. It can be anything. But let's get back to, let's put it as n only. So now we are in function main, and so now we are on line 24. So on line 24, it's an expression, and on the right hand side of the expression, that assignment statement, on the right hand side of the assignment statement, we are uh, executing, we are calling the function readin. In order to break through, in order to trace the execution of the instructions of yeah, step I, or I think next I, yeah, or step I. Yeah, okay, step I. So now we are into readin. So if you use this command called as bt, you can see what it says is bt stands for backtrace, that it says that the function readin is called in function main. Step by, if you don't use step by, what happens is instead of tracing the individual steps of the readin function, the whole readin function will be executed in one shot. I will show what step by does. So let's focus here. So are you with me here on the message that you are seeing when we do a bt command? Bt stands for backtrace. So what it says is that the function uh, readin is called, that the function readin is called on line 24 uh, of in this file in function main. So if you go here, you can see this. On line 24, readin function is called by the function main. So, so main is called as a caller function. Main is called as caller. This is called as caller, and readin in this particular case, it is called as call. Are you good here so far? Don't worry about that big number. So it's you'll just ignore it for the time being. Explain. BT just tells you which function is calling which. So when we do a BT, it is telling, so right now we stopped our program execution on line number 5. And when we do BT, it tells that the main function call is calling readin, and we are in the readin function. So let's go through this and then we'll come back again. I'll try to explain. Now we are going to execute the next. Okay, so now I have next, and then it asks for what is the next number. Let's say we enter 12. It checks if n is equal to 12. If n is equal to 12, no. So you go back and it says return n. So if you see print n, so it is returning the value 12 to the function which is calling. So now after we come back here, so next we come out of this function. So when we come out of this function, so line number 24, so if you now see print n, so this n is the no, this n is the local variable n of the function, and then we come out, and then we exit. That's it. Or you're, how many of you are with me here on this trace on the high level semantics? So we are calling the function readin. We are calling the function readin, and the function readin is returning a value, and it is of type integer, and it is returning that value on line number 16. What do you mean by scope of exit 0? Exit is a function call which terminates the program. That's all. Exit doesn't have any scope. What do you 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 forget about GDB commands, guys? Like, can you understand the semantics of the main idea? The main idea is So this is what you need to learn, what to focus on. Okay, and then we look at no, we will uh, we will look at the details later. But what is the main idea here? The main idea here is on line number 24, we are calling a function, and that the statements of that function gets executed. And there are two possibilities there. One possibility is if the input number is equal to 1, then no, we will exit out from the program. We don't return from the function at all. But on the contrary, if we enter a number which is other than 1, then that value will be returned to the main on line number 24. And that returned value is assigned to the local variable n on line number 24. This is the most core idea. That is idea 1. Idea 2 is the variable n on line number 6. It's a local variable for the readn function. And the variable n on line number 22, it is a local variable for the main function. And these two local variables, they have different memory addresses, and they are completely independent of each other. The scope of a local variable is the function in which it is declared. Are you all with me on these important ideas on this? And then once these ideas are clear, then I'll address the rest of the questions. Okay. So now let's compile this code again. So there is this question. So GCC minus G same prime function dot C VDB a dot out. Right. So now we are on line number 24. Pay attention to me. If I just press next, what happens is we don't trace the statements of the function readn. Readn gets executed. Like for example, just like how printf gets executed, just like how scanf gets executed, we don't trace through the steps of the individual statements of the readn function. If I just use next. This is what is called as a step over. So in when we are using GDB, there are two options when you get a function call. When you get a function call, there are two ways to trace the function call execution. One is called as a step over, where we don't. Other is called as a step inside. So when we do step over, that's what we did. So we don't kind of trace the individual instructions of the function. The whole function just gets executed like that. And when the readn function is getting executed, it is asking for what is the input value number. And let's say we give 4, then we are out. So we don't see what is happening inside readn. But on the contrary, let's try to run this program again. Let's try to run this program. Step over means that the whole function gets executed in a single shot. In the sense let's see now here. So we are on line number 21. So we see next. So if I do step inside, then we will be tracing the instructions. We will be tracing the individual statements of the readn function. So when I do step I, we go to line number 5. Because now we want to go to the individual steps of the readn function and see how they are progressing. And then again we do next, and then we do next. And so like for example here on scanf, when we do next, we kind of execute scanf. We don't try to trace the individual statements of scanf. So Sanyam has this question: if you do step I inside printf for scanf, so the thing with printf and scanf are they are library functions, and the source code for them will not be available. So when we do step I, what happens is you will end up tracing the assembly language instructions of printf and scanf because the source code is not available. Like for example, now if I do step I, uh, yeah, it's not allowed even actually, looks like. Yeah, because the source code for scanf is not available. Are you with me here on the Sunny? So we cannot do a step by on printf and scanf. So you enter 45 and then you come out, and then you are not, so you check if n is equal to 1, no, and you return n, and so now here we are on line number 26. So now let's try to run the program again. So when we try to run the program again, uh, next step, I step inside, and then next. So when it asks, I'm entering 1. So now the value of n is equal to 1. So what happens if n is equal to 1? Which statement, what will be the next statement that gets executed? The next statement that gets executed is the one on line number 12, right? So printf gets executed, and then so now since we are calling the exit function, you will exit the program. You'll exit the program. You don't come back to the main function. You don't come back to the main function because you are exiting from the program. That is how exit works. When you hit an exit statement, you will come out of the whole program execution gets terminated. You will come out of the program. Are you all with me here so far? So now there is this question on backtrace, which let's try to uh, run this program again. So now we are in function main. So when we do backtrace, that means we are function. So we are in function main. We are, so 0 in exit is a written code. For the time being, don't worry about it. You can give either 0 or 1 or so right now BT means backtrace. So it tells us what is the function in which we are in, and so we are in right now in the function main. Okay, so now so we are on line number 24, and so we step inside. So now when we step inside, when we do BT, what it says is now we are in function readn, and readn is called by main, and it is called on line number 24 of the source code file. Are you with me on BT now? We are in readn, and readn is called by main, and that is the information which the BT command is printing. Are you all with me here, guys? Is it okay? So now let's keep going. So printf, let's say I enter 12. Next. And then, now also let's do BT. We are still in readn function. And then when we come next, you are, let's see, we are still in return from the readn. So now we are back from readn, and when we do a BT, what happens? Now we are in main again. So, and that's what it says. This is what is called as a call stack. This is what is called as a call stack. So shall I proceed further? So shall we continue and write the rest of the code? You understood what is happening here, right? Main is a very special function. Okay, main is a special function, and yeah, it is required for your program to execute. So think of it as a main has some. It is main is not a keyword; it's a special function. And so now let's go back here. So now what we would like to do is we will visit what is called as call stack later, but just take it like this. So here what is happening is, if you see, so here You have main, and then main calls, readn. So in your program, there is what is called as a stack, which you don't see explicitly. And so associated with main, there is this, think of this as a memory. Think of this as a memory. So the information associated with main will be stored here. And when main calls readn, we will revisit this idea later. For the time being, I'll just give a quick view. And so when main calls readn, what happens is this is the stack associated. This part of the stack is associated with readn. So why is it called as a stack? Like if you have a stack of plates, when there is a new plate, you keep the plate on the top of that existing stack of plates, right? Like when you go to buffet in hotels, in restaurants. So what happens? So they have a stack of plates, and when they are running out of plates, they bring a new stack of plates and put them on the top. And then this still corresponds to me. So we will see what call stack is later, but the way it gets printed in GDB is it says you have main, and then on the top of main you have readn. That's what gets printed. So when we are in readn, so that's what we have seen in the GDB uh, program. So now let's try to see. So now the next thing that we would like to do is we would like to check if the number is prime or not. Okay. So how do we check? We would like to check is now I want to use a new data type called as bool. Okay. So is prime. So this should, and it takes a number as a parameter. It takes a number as a parameter, and then what do we do? So what we are doing is what is called as a code refactoring. What we are doing is what we are doing is what is called as a code refactoring. So I'm introducing a new data type called as bool, which is defined in stdbool.h. And then finally, so what it does is initially we think that the number is not prime. And once we find a factor, we declare that number as a prime. And then so finally we return uh, are you with me on this function? What we are doing? So here we are passing a parameter. No, if there is a factor, then it is not a prime. No? Initially, we think of it as not a prime. No, please pay attention here. So this function now, it's a different kind of, it takes one parameter. The type of this parameter that it takes is integer. This is what is called as a parameter, and this is what is called as a return type. This is a parameter, this is a return type. So when we call this function is prime, let's say with 10, it should return true. It should return false because 10 is not prime. And similarly, when we call this is prime with a value 7, it should return true because 7 is a prime number. So the return value that is written by this is prime function, it is of type bool. Oh, it should be initialized to, okay, got it. So initially we think it is a prime, and then later on we cannot have any guarantee if we don't initialize it anything. Initially we think of it as a prime, and once we find a factor, we declare it as a not a prime number. Of course, this number, this will give us, if you if the input is 7, this function is supposed to return true. Are you all with me here on this code, on this function code? How many of you are with me? That the important thing is it takes a parameter which is of type integer, and it returns a value which is of type bool. It is possible to use return true, return false, all those things, no problem. But we are doing, this is the logic that we have. So now what we do is here, we call this function is prime. And then what we do, so here we can just check if is prime. We don't actually need to do anything if it is equal to prime. Let me do this. No. So this is the code. So if n is a prime number, then is prime returns true. So the condition for if also becomes true. So we say it is a prime number, otherwise it's a composite number. Are you with me in this code? You're all good? From line number 40 to 43 to 46, you're happy with the code that you are seeing on line number 43 to 46? All right. So let's compile this code and see what happens. So GCC minus G prime. Yeah, so that's it. So now let's try to GDB this code and see what is happening. So now, can you tell me what will be the, so now where are we in now? Where are we in, which function are we in? So we are in main, so now after when main calls readn, what will be the, how does the call stack look like? So there is information for main, on the top of that readn will be sitting. Yes or no? So we move from this state to this state. This is the call stack state. Call stack state. Great. So now let's go to, so now because of that, when we do BT, you will see call. So here right now we still didn't yet call it. So this is what gets printed. So now let's do one thing. So now let's do step I. That is, we want to trace the individual instructions or the statements of the readn function. So we do a step I. And so after we do a step I, when you do BT, you will see that the call stack has changed from readn is sitting on the top of me. Are you with me here on this one? The display of BT, how it is changing? Good. So now let's do next, enter no n. Let's enter 12 and next. So now after we come out here, if you do a call stack, since we are out of the readn got, so this is what is called as a pushing read and push read and the information associated with read and gets pushed on the call stack. So now what happens is, now after we are out of read and the call stack state will be like this. So now if you do BT, so you can see it's only main. So now again when we do step I, we enter step I, why it is not working? Okay. So now we are inside step I, inside this is prime. So now when you do BT, we will see that main is calling is prime. So the state of the call stack is like this. Main is prime is present. The important thing I want you to understand here is, again, the address of the variable, the n that you are seeing here, it is like a local variable to the function is prime. It is like a local variable. It is like a local variable to the function is prime. So this is, if you see this n here, this is like a local variable to is prime, and its scope is restricted to is prime. The only difference is when is prime is called, the initial value of n is set to the value that is being passed by the function call. This is the value that is being passed by the function call. Are you with me here? So the main difference here is the value n, let's say if the value of n is 12, this 12 is copied into this version of the 12 on line number 20. So otherwise, apart from that, the parameter n here that you are seeing, this is what is called as a parameter n. It is like an equal local variable to the function is prime. It is a local variable to the function is prime. It's not the position of the stacks, it's the state of the stacks. Okay, so the local variable n, it gets, its n is equivalent to a local variable, except the fact that the initial value of n is equal to the value of n that we are passing as an argument. So here we are passing some value as an argument, and that value will be copied into. Don't worry about a push and all. So just focus on what I'm saying. Okay. In fact, I will just remove this thing. We'll revisit these ideas. I don't want to introduce many ideas at a time. All I want you to understand is, the state of what is called as a call stack. So now, if you see, let's go back to our GDB program. So now where are we? So we are in this function is prime. And if you do a BT, you will see that main is calling is prime. And that's what the stack trace. That is the semantics. That is not the value of n that is b. Whatever, no, if n is equal to, instead of this, if I just call 10, no, then 10 will be copied into the local variable version n of is prime. There is no binding between the local variable n on line number 39. Whatever that is being passed as an argument, that argument value will be copied into n. Like on line 20, you can see, if I call it with 10, then when is prime gets invoked, then n contains 10. Does it make sense, guys? Are you with me here? Okay. So now let's keep going. Next. And then you keep, so since n is equal to 12, so it immediately 12 is divisible by 2, so prime is equal to false. And when we hit the break statement, we break from the outermost, the innermost for loop. The innermost for loop is the one that is there on line number 24. We come out of it, we go to return prime. So if you do print prime, you see it is equal to false. And when you go to next, yeah, so You are on line number 46. And then if you do a BT, you will see that is prime is no longer on the stack. So what happens is, so the state of the call stack is you just have the main. That's it. And then you do next is you print the 12 is composite and you come out of the code. We don't need this variable prime here. We don't need this. Are you with me on this whole exercise, what we did today? Do you understand this idea of function parameters and where is this here? So now what so the reason I introduced functions early is you can start using them nicely to write your code in a modular fashion. So this is what is called as what we did today. This class is interesting. That is, we started with code like this where everything is in one place, and we kind of rehashed the code and nicely kept it. So now we have readn function and we have isPrime function, and if you see the main function which is clean. Doesn't this code look good? It's much more cleaner, right? Than the other code where everything is in one place. And this is what is called as code refactoring. Code refactoring. Code refactoring. Okay. So we will stop the discussion here for today. And in the next class,